So hydrogen bonds are these attractive forces. They're actually intermolecular forces, but they're a special type of intermolecular force. These are between a hydrogen atom and a significantly electronegative atom. Okay? There's only 3 electronegative atoms that hydrogen will bond to. And they're up on the board. So it's hydrogen and nitrogen, hydrogen and oxygen, and hydrogen and fluorine. There's only 3 elements that can be involved in a hydrogen bond: oxygen, fluorine, and nitrogen. You will not find a hydrogen bond in anything else. And when you look at them, this shows you water molecules, and the little blue dots are your hydrogens, and the red dot is your oxygen. So this blue hydrogen is attracted to this negative oxygen. That's a hydrogen bond right there. This blue hydrogen, this red oxygen, hydrogen bond. These are my covalent bonds. It's the dashed lines we're looking at. They're the intermolecular forces that hold these molecules together. But hydrogen bonds are a special class. Okay? There are all kinds of forces. There are London dispersion forces, there are dipole forces, there are van der Waals forces. We're only going to talk about hydrogen bonds. That's all we care about. Okay? Excuse me a minute. May I cut in here? I don't know. Can I call you back? Okay. Bye. Okay. So we ready? Okay. So hydrogen bonds. That's a quick little video about hydrogen bonding. Pay attention. There are a couple of things. I would probably take some notes from this, because this is also stuff that might be included in a test.
How come some insects are able to walk on the surface of a pond, but you quickly sink to the bottom when you try to walk on water? And why do lakes freeze from the top down in winter? In a word, the answer to all of these questions is polarity. Water is a simple molecule made up of 1 oxygen atom and 2 hydrogen atoms, but it is essential to life. In fact, water makes up approximately 60% of the adult human being's body weight. The polarity within those water molecules gives this common substance the properties that make it unique and life-sustaining. Polarity refers to the unequal sharing of electrons within a molecule. For water, the bonding between the oxygen atom and 2 hydrogen atoms within a single water molecule is like a tug of war between a big, strong football player and a cute little toddler. Oxygen is a larger atom with more protons in its nucleus than hydrogen. These positive charges are like a person's physical strength. They are able to attract the negatively charged electrons in the bond, just like a strong individual is able to overpower a weaker individual in a tug of war. So, oxygen is able to attract more than its fair share of electrons. Because hydrogen is smaller and has less strength, or fewer protons, it loses the tug of war and attracts fewer than its fair share of electrons. So the oxygen in water behaves as though it's negative, and the hydrogens behave as though they're positive. The bonds within a single water molecule are called polar covalent bonds. Covalent means that the electrons are shared. But, as we just learned, polar means that these electrons are not shared equally. In water, the oxygen acts negative, and the hydrogens act positive. Since negative and positive attract, that oxygen is attracted to the hydrogen atoms in neighboring water molecules. A special type of bond forms between water molecules, known as a hydrogen bond. Hydrogen bonds don't just happen in water either. They can form between a water molecule and different substances that are polar or ionic. Water's ability to stick to itself is called cohesion, while water's ability to stick to other substances is called adhesion. Now, think back to the initial questions. First, why are some insects able to walk on water? Surface tension due to hydrogen bonding creates a thin film on the surface of water that gives enough resistance for super light insects to walk on. You can't walk on it because the hydrogen bonds aren't strong enough to hold you up. Why does ice float on top of liquid water? For most other substances, the solid state is more dense than the liquid state. But that is not the case for water. Hydrogen bonds keep water molecules farther apart in frozen water than in liquid water. The farther apart the molecules are, the less dense that solid is. So ice is about 9% less dense than water, which means it floats on the top. That's why lakes freeze from the top down and aquatic life is able to survive through a cold winter every year. It is the polarity of the water molecule and the resulting hydrogen bonding that account for water's unique properties. So, the reason that water is so special, from inside your cells to the world's oceans, is simply because it is a polar molecule.
Okay. Just like I said before. Yay. So water is a polar molecule. Water is very unique. And thank goodness it is, because it helps us live here on Earth. These hydrogen bonds that form between this oxygen and that hydrogen, these are hydrogen bonds. They are very attracted to each other. So when I add some heat to this, they begin to vibrate. They vibrate, and as they vibrate and they vibrate and they vibrate, they come apart and they go from a solid to a liquid to a gas. One thing about water and hydrogen bonds is this. It takes a lot of energy to break those hydrogen bonds in liquid water. Water can hold a whole lot of heat, a whole lot of energy before it comes apart. Water has got one of the highest specific heats that we know of, 4.184. It takes that much energy, it'll hold that much energy before it turns into a gas. That's why our planet has life on it, because water holds heat, and it holds heat around the Earth like a blanket and stays warm enough for us to live. If not, we'd all be freezing to death. Also, water is, most of what we're made up of. The hydrogen bonds, it helps us keep our cool. Okay, so when we heat up, it helps cool us down as well. Water is so important, obviously, for life and everything else. Not to mention, it's a lot of fun as well. So if you look back here, I don't know if you'll follow me this far back or not, but if you look back here, I have a jar with a screen on it. I think it lost it. Come on. Can you turn around? There we go. There we go. Okay, so if I fill this jug up with water, I don't know why I did that for, that was kind of dumb. It's got a screen, I don't need to do that. Alright, so I'm going to get this thing on nice and tight. So if I fill this up full of water, okay, and I bring it over here. Okay, I take a piece of plastic board and put it like this. I turn it over. That's it for a minute to get it set. The water stays in the jug. Why? Because of the surface tension of water. Water's made, I know there's a screen in there, that's just to kind of help. But water's making like this lattice, this net. They like each other so much, they generate this net between them, and they can actually hold back all, this is kind of heavy, you can see my hand, it's kind of shaking. You can hold back all of that water. Right? That way, give it a little air, the whole thing goes away. Isn't that fun? And then, prior to technology, our idea of having fun in the summer was, we called it poor man's Jenga, if you want to look at it that way. We'd put a lot of water into a cup. You go get some plastic cups or a cup from the kitchen, and you fill up as much as you can. You spill it like I do. And you sit it down, and instead of playing Jenga, you take things like toothpicks or popsicle sticks and things like that, and we'd say, okay, you got to float it on top. Whoop, I'm terrible at this, obviously. and you float it on top, and then the next person will have to go. And you just keep doing it to see who could keep floating these things on top. Whoop, not like that though. But yeah, so water is so cool. Whoop, I'm terrible at this obviously. But then what's so fun then is if you take a drop of Dawn dish detergent and you put near it, they all sink because it disturbs the hydrogen bonds in water. So you can have a bunch of paper clips floating on top. I mean, you can get maybe like 6 or 7 floating there, and a drop of Dawn dish detergent, they all fall. Because it's called a surfactant. It disrupts the surface tension. Fun, huh? It's kind of neat. Yeah, poor man's Jenga. That's we didn't have technology, and I didn't have Jenga or games, so we'd make up things like that. Okay, let's see. So if we go back over here, let me get this thing rearranged again. Oop. Nope, I'm wrong way. Right. I wish it had a setting to go back to like your original place. Okay, so that's hydrogen bonds with ice. You see, as they come apart, they become less dense because they spread themselves out. That's why ice floats. Very few other solids ever float, but ice will float in itself because the hydrogen bonds keep them at a certain distance. Now, your DNA has hydrogen bonds as well, thank goodness. So here's hydrogen to oxygen, nitrogen to hydrogen, oxygen to hydrogen. So your base pairs are held together by these hydrogen bonds. Okay. Now what you need to know for the test about this stuff, here's a wonderful comparison of ionic and covalent bonds. So ionic, the complete transfer of electrons, where polars are unequal sharing, nonpolars equal sharing, full ionic charges, partial ionic charges, no charges, and a metal, and then 2 nonmetals. And this also shows it as well. It's kind of like this one because it actually shows you like the line. So they transfer electrons over, they share unequally, and they share equally. And also this chart here is a wonderful comparison between an ionic bond and a covalent bond as to these different characteristics. I would definitely study this chart for the test. 8.4. Okay? Now, the fun part of this kind of stuff. Have you ever heard the term like dissolves like? Have you ever heard that? Well, like dissolves like. If I have a polar compound, only a polar solvent can dissolve it. If I have a nonpolar compound, only a nonpolar solvent can dissolve it. So I cannot dissolve a nonpolar compound with a polar solvent. It can't happen, or the other way around. Water is a polar molecule. Most of the things, like, let's talk about P&G. P&G makes soaps. They're pretty smart about it. They know if you wash your clothes in just water, they're not going to be clean. Your body odor, your sweat, the dirt that comes off of you, either blood or grime or coffee or food, those are all non-polar materials. Your body oil. Oil is a non-polar material. Water is not going to dissolve any of those things. You can wash your clothes, but they're not going to be clean because water cannot touch any of those things. So we need something that's going to help us get that clean out. So what we have is this stuff here. Oh, here's water and oil don't mix. So here's the oil layer. It's a big non-polar. Oil is non-polar. Water is extremely polar. They'll never mix. But what P&G figured out, and what actually pioneers figured out a long time ago, is if you take animal fat and you mix it with some very, very strong base, you can make a substance that will actually clean you and your clothes and other things. This substance is called a micelle. You have this water-loving head, okay? This guy likes water. This guy is a water-hating tail. This end is polar. This end is nonpolar. It has two different ends to it. So these are nonpolar. This is polar. So what happens, according to this little cartoon strip, come on, Grime, let's get going. No. It's like a pile of poo, kind of. That's the other thing yesterday. I had my poop socks on when I had to go to the hospital. Everyone in the hospital thought it was pretty funny. Wearing my poop socks. Like, oh, good grief. Anyway, so come on, Grime, let's get going. No. Soap, I need you. So that's the water molecule screaming for soap's help. Here comes the soap. It looks like a little balloon floating in. And what happens is this water-loving head, this polar head, likes the water molecules, so it goes in. The tails like the dirt. So the tails kind of get up and arrange themselves and embed themselves in the dirt. And then when the water flows away, it takes the dirt with it. That's how soap works. Okay? And thank goodness we have this because now we can clean ourselves. Okay? They're all made of the animal fats and things like that. And I like this. Help, help, I'm dissolving. But bears are insoluble. That's easy for you to say. You're not a polar bear. Get it? Water's polar. The bear is polar. He dissolves in the water. So, I thought it was funny. But anyway, so that is the end of our unit. Are we okay? So if you're not here, make sure you go on to the Schoology site, chapter 7, 8, 9, and you look at the practice test and all the stuff on the review page. Okay?